So firstly, just some information about CIGRE as a bit of an introduction. So CIGRE is the world's leading knowledge development and sharing program for power system expertise. It is a collaborative global community and has presence in over 100 countries, headquartered in Paris, France. The Next Generation Network, or the NGN, is a subgroup established for young members, providing networking and development opportunities for professionals under 35 years of age. You can get involved by sending us an email, and you can also become an active member of a working group or study committee where you can present your work and identify opportunities in your area of expertise. So please keep an eye out for future events on the NGN website. There's also information on there about how to join the NGN as well. We usually do quite a few webinars per year. There's also an NGN social event later tonight as well. So all that information is on our website. Also, it's just a bit of a heads up that submissions for the Australian CIGRE NGN nominations for the 2022 Paris Session NGN Showcase are now open. This is a great opportunity for young members to present in front of international experts and gain recognition. Applicants are to prepare a presentation and a paper in the area of one of the CIGRE preferred subjects for the 2022 session. And this is the 5th NGN showcase and has become a cornerstone of the Paris sessions in recent years. This information is also on our website, so feel free to have a look at that. So now I'd like to introduce our presenter for today. So as I said, we're lucky enough to have Michael from Transpower here to talk about his experience with Line Commutated Converter HVDC transmission. So Transpower, as many of you would know, is the owns and operates the high voltage transmission network in New Zealand, including the HVDC LCC link connecting the North and South Islands. Michael graduated from Canterbury University with a degree in electrical and electronic engineering in 2008. He currently works for Transpower in New Zealand as HVDC and Power Electronics Engineering Manager, leading a team of engineers to operate and maintain Transpower's HVDC and Power Electronic assets. Prior to holding this role, he worked as an engineer on the Pole 3 project upgrade of the New Zealand into Ireland HVDC link, which was commissioned in 2013. Recently, he received the Young Engineer of the Year Award 2019 from the Electricity Engineers Association in New Zealand. He's also an observer member of the CIGRE B4 panel. So without further ado, I'll hand over to Michael. Mike, do you want to try and share your screen?
Yep, thanks Maddie, and thanks for the introduction, and yeah, welcome everyone. Thanks for coming along. Yeah, I hope it's a good day over in Australia. It's pretty miserable here in Wellington, New Zealand. It's pouring down. That's all good. So I'll just try share my screen and we can get started. Is that coming through, Maddie?
Not quite yet.
Here we go. I'll try again. It didn't work.
We can see your screen now.
Is that better?
Yep.
Yep, that's good. Thanks, Mike.
Excellent, thanks. All right, we'll get started. So yeah, first of all, I just have to give some credit to the company in Canada called TransGrid Solutions, who've kindly given me permission to use some of their training material that I used to put together these slides. It saved me a lot of work, so yeah, thanks to them for that. But I'll get on to the agenda. So for the presentation, so we'll start off with some HVDC history. I'll go through the applications, advantages of HVDC. I'll talk about the converter configurations. Up to that point, I will be sort of talking about LCC and VSC a little bit, which is the new kid on the block. But then from there, I'll only be talking about LCC. So we'll go into the LCC converter operation, the LCC station equipment, and the virtual Benmore site tour. So I've got some 3D photos that I'll try and present. We'll see how it works. I'm not sure if the performance is going to be okay, but hopefully we'll be able to get something out of it. Yeah, I should also mention, talking about the VSC voltage source converters, Les Brand did an excellent presentation last year for the NGN on the voltage source converters, so I'd highly recommend watching that one as well. That's on YouTube if you're interested. So I'll try not to overlap too much with what Les covered in his presentation, but I'll just cover the relevant bits and pieces. All right, so HVDC history. So electric power generation and transmission, it actually started in DC in the 1800s. So from the late 19th and early 20th century, they did have these ways for DC transmission where you just basically had these DC generators, and you connect them all up in series, and then send it down the transmission line, and then you can run the motors at the other end. So that was called a Thyristor system. Yeah, they could get voltages pretty high, actually, 150 kV. And they could get up to 200 Ks, which is actually pretty impressive considering. But yeah, obviously the losses weren't great. And yeah, there's all sorts of issues with the machines, with, you know, brush wear and all that sort of thing. So we moved on to something better. So there's a guy called Uno Lamb. He's sort of known as the father of HVDC. He's a Swede. But yeah, Dr. Lamb and his research team, they developed a 50 kV and 100 amp mercury arc valve. And in 1954, these were used for the first time for a transmission link to Gotland, which is an island off the mainland of Sweden. And that was a 100 kV, 20 megawatt transmission scheme with almost 100 Ks of cable. And there's the man himself. So yeah, he's pretty famous in the HVDC world. There's an award called the Uno Lamb Award that the IEEE awards, and that'll be almost the most prestigious award you can get in HVDC in the world. I had to put a plug in for the New Zealand scheme, of course. In 1965, the New Zealand Inter-Island scheme was commissioned. So this was a 250 kV, 600 megawatt scheme. So you can see it's quite a big step up in the power there and the voltage. So New Zealand scheme was wasn't the first scheme, but it was one of the first big schemes. And we've got a 40 kilometer submarine cable. And that was a bipolar scheme using these mercury arc valves. So the first Thyristor valves were introduced in 1972. And they've pretty much completely replaced the mercury arc valves due to the reduced maintenance requirements and improved reliability. So the mercury arc valves used to require a lot of conditioning. You pretty much always had to have one of the valves out being conditioned to make sure they continued to run correctly. And they did suffer from things called arcbacks. I remember when I first started, we still had the mercury arc valves and we used to have issues with those. But yeah, going to the Thyristors pretty much eliminates those problems. And now with the Thyristors, there's a system in the world in China that is plus or minus 1100 kV and 12 gigawatts utilizing Thyristors. So you can see how far things have come. That scheme was commissioned in 2019. So the present systems that are available for HVDC, so you can still buy the line commutated converters. They've been around for a long time, but the main benefit we still have with the LCC is the low losses. but after that, it's pretty much all negatives. So you need to have a strong AC system, especially at the inverter with LCC. LCC also has a minimum power limit, and it has harmonic and reactive power issues, which we'll go into in more detail later. And I'll briefly talk about voltage source converters. They're sort of the new kid on the block. They're utilising IGBTs, switching devices, so they've got turn-off capability. And because of that, they're good for feeding weak AC networks. They also act as StatComs. Each converter station can pretty much be a StatCom and help with regulating your AC voltage. It's quite the contrary to the LCC, which generally does bad things for your voltage. They can also do black start, voltage source converter. You can't do black start with LCC. And the other thing with the voltage source converter is you don't need to do polarity reversals on your transmission line or cable when you do a power direction change. So on LCC you do, the current stays the same on a LCC and you change the voltage to achieve a power reversal. But on a VSC it's the other way around. The voltage stays the same and you change the direction of the current. So that has some benefits for cables, especially XLPE cables. So XLPE cables don't like polarity reversals. So generally if you have an LCC link, you have to go with the older mass impregnated, the oil cables. So paper oil, lead sheath sort of thing, and they can handle the polarity reversals, whereas the XLPE can't. So if you've got a really long cable, the XLPE cable is quite a bit cheaper. So generally you'll find the long cable links, they'll try go VSC if they can to save on cable costs. Yeah. All right, so we'll talk about some of the applications of HVDC. So what's it good for? Why would you go HVDC over just an AC link? So if you want to transfer a lot of power from remote generation to a load center, like and China's a pretty good example of that. They've got a lot of these huge hydro stations on the Yangtze River, going out to the big cities like Shanghai, etc. So China's got a lot of HVDC, and you can see that they're all pretty big. We're getting up to some 800 kV schemes, 6 gigawatts. Yeah, they're big players. There's also this graph that gets pulled out quite a bit. So once you get over a certain distance, it is actually cheaper to go HVDC instead of AC, and that's due to the losses. Yeah, if you capitalize the losses over the lifetime of the link. So you can see with the HVDC there is an entry cost, and that's basically your converters. So you have to buy your converter stations at each end. So that's pretty much a steady cost. And then as your distance goes up, that's the cost of your line going up. So with AC, you start pretty cheap. You've just got to probably get a transformer, or maybe not even that, just a spare bay. And then this is your cost of your lines and your capitalized losses. And if you add some series compensation, that can bring it up, make it a little bit better. But again, you've got to you've got to pay for that series cap. So there is a point where HVDC will be cheaper, and that's sort of it's sort of hard to put a number on it, but I'd have to say probably around 800 to 1,000 Ks you'd be getting there. Yeah, there's other things to consider, of course, as well, but we'll go into those. So yeah, one of them is the towers that you need for HVDC. So for a given power rating, you can have a much smaller tower, much smaller right of way. So you can see this one HVDC tower with a bipole on it. So you have one pole on this side, one pole on that side. Compared with this double circuit AC tower, it's quite a bit smaller, like not as high, not as wide. So you need less land if you're building a new line, less easement, all that sort of stuff. It's just showing that again. The other reason to use HVDC is submarine cable transmission, or actually any cable transmission, to be honest. You can see a few examples of that in Northern Europe. This diagram's a little bit old. There's actually a couple more now. But the main reason for using HVDC for cables is the charging current that you get with AC cables. So AC cables are limited in length due to the charging current. Cables have got quite a lot of capacitance compared to, say, a transmission line. With the HVDC cable, you've got no length limitation at all. It could be as long as you want. This table is just showing some values that were pulled out for a 500 kV XLPE cable. You can see that for this particular cable, you know, once you get up to 70 or 80 Ks in length, you're completely consuming the cable's rating just in charging current. So you've got no ability to send any more power on that cable at those lengths. And I can tell you this is a land cable, but for submarine cables, it's even worse. They tend to have even higher capacitance. So, yep. So HVDC, that's pretty much the main reason HVDC was adopted in New Zealand, was because of that submarine cable crossing. You can also use HVDC to connect systems with different frequencies. That can be quite handy if you've got different, you're on the border with a country that's got a different frequency, or you use different frequencies within your country. Japan's an example of that. There's also Argentina, Brazil, they've got a system there. You can also use it to connect asynchronous systems, so you can have the same frequency but not be synchronized. Yeah, it doesn't matter with HVDC, it can handle that, no problem. So yeah, in summary, applications, if you want to move a lot of power over a long distance, if you want to move power by cable over even moderate to long distance, and you could even say short distances, to be honest, the charging current is quite a problem on AC, and it gets worse as the voltage goes up. Yeah, if you want to transfer power between asynchronous systems, if you've got congested transmission corridors, or it's hard to get your easements, then HVDC is good. And the other thing is with the HVDC, you can choose your power. So it's not the power on an AC line is determined by the physics, the angle difference and the voltage magnitude difference between the 2 points, and that will just determine your power flow. Whereas with the HVDC, you can choose exactly how much power you want to send, as long as the sending end and the receiving end networks can supply and receive it, it'll be able to do it. So you can manipulate the power flows, and sometimes you can use HVDC to offload AC lines or improve things, so it can be used for that. Yep. So yeah, some more advantages. Yeah, that controlled power exchange that I was just talking about. You can limit your short circuit currents between, so if you'd used an AC network connection, you can increase the fault level, which can be, a bad thing that can end up costing you more in gear. With HVDC, you're not gonna do that. It's completely separated. With the HVDC, you can also do transmission at reduced voltages. So here in New Zealand, we normally operate at 350 kV, but we can operate at 250 if we want. And that can be handy if we've got problems on the line, like contamination on bushings, or where we're getting flashovers. We can just go to reduced voltage, and it restricts the power we can send, but at least we can still send something. Whereas with the AC line, it's either in or it's out, and you can't have sort of 50%. HVDC, you can do the overloads. Our system's got some pretty good overloads to deal with loss of a pole in bipolar operation. The remaining pole can overload to try and take up that power. Also, you get no fault cascading, so that's the when faults can cascade through an AC network at a HVDC. If it's designed correctly, you can stop it at one end. So, for example, if we had a collapse in the North Island, it shouldn't affect the South Island, as long as the controls are done correctly. And yeah, the other advantage is black start, but yeah, you can only do that with the voltage source converter, not with LCC. All right, so we'll talk about some converter configurations that you can have. Yep, so we'll go through those. So for the long distance transmission, 2-terminal. So I just have to say for the LCC, 2-terminal is pretty much 99% of the installations in the world. you'll have a sending end and a receiving end, and yeah, you can change it around if you want, depending on what your circumstances. In New Zealand, we do change the power direction quite a bit, sort of about 30% of the time might be going south, but yeah, 70% would be going north. But some other schemes will only ever go in one direction, just for there might be a big generator at one end and a load at the other, so you're never going to do reverse power. But anyway, this diagram here is showing a two-terminal system. You have the sending end here, receiving end here, with a metallic return scheme. So you have a high voltage conductor on the top, and then you'll just have a low voltage wire going back to your sending end. You can also do earth return with HVDC. So earth return is quite cool because it means you can transfer power with just one wire between your sites. So that reduces the cost of your transmission line. It also reduces your losses because in the New Zealand example, our main transmission line is about 13 ohms between Haywards and Benmore. But if you take the earth return path, it's only about 0.5 ohms because the earth's, dirt's not a great conductor on its own, but when you've got, thousands of square kilometers of it, it's actually pretty good. So yeah, the losses are pretty good, much improved in monopole with earth return. The only issue is you can have some environmental concerns when you do earth return. You can end up with current going places where you don't want it to, like it can go into nearby buried structures and cause corrosion and fencing or pipelines. And it can also go up into your AC network through grounded neutrals and cause saturation of the transformers. So a lot of jurisdictions don't allow it. We do have it in New Zealand, but mainly just because we've always had it since 1965. And we do suffer some of those issues I mentioned, but it is possible to mitigate them. And I think the savings and losses are worth it. Yeah, the whole ground return thing is a subject in itself, so I won't get too bogged down. But yeah, this is a two-terminal bipolar scheme with earth return. So this is the scheme that we have here in New Zealand. So we've got two poles here with the earth in the middle. One pole runs at positive polarity, the other pole runs at negative polarity, and you have this current that goes, and the current always goes in the same direction around the loop, regardless of which way you're sending power. And if you want to change the power direction, you change the voltage on your conductor. So if you're balanced, if each pole is sending the same amount of current, then you can see we'll have no current in the earth return path. And that's the way we operate here in New Zealand most of the time. The poles are balanced and we'll have no earth return current. But if one of the poles trips for whatever reason, it will then go, the full current will then go into the earth, and we'll be able to maintain transfer with just one pole. Yeah, the other option is to have a metallic return here, so you run another cable between your stations. So that has to be the same thickness, right? Because it's carrying the same current, so it can still be quite expensive, but you can save on the insulation. You don't need nearly as much insulation because you're only sort of going to be dealing with 1,000 or 2,000 volts sort of thing. Okay. Now this is for the really big HVDC bipoles. Use this configuration, so they call it series group, and so that allows you to basically take you put sort of 2 valve halls in series per pole, and you have these bypass switches. So it allows you to basically stack it up. So if we've got plus or minus 350 kV. If we duplicated one of the valve halls, we could get 700 at the same current. And that's basically what's being achieved here. And a lot of those big links in China use this configuration. Multi-terminal. So yeah, as I said before, it'd be probably less than 1% of schemes, LCC schemes, that use multi-terminals, because it's quite problematic. It's a lot of the controls become really complex, even with only 3 terminals. And if you have AC faults, that's going to impact your power transmission at all of your terminals, which isn't ideal. So multi-terminal's been done a lot more with voltage source converters lately, and it actually works pretty good with voltage source converters. There have even been some hybrid systems where the sending end or the rectifier will be a LCC, and then they'll have multiple VSC taps coming off. And that seems to be working pretty well as well. So you take advantage of the low losses of LCC at your rectifier and invert with the VSCs. But yeah, included for completion. The other configuration is back-to-back. So this is basically, you just don't have a transmission line. So you have both of your sort of converter stations at the same site. And that's mainly used to connect your asynchronous or different frequency AC systems. So these are relatively common. There's maybe 10% would be back-to-backs. Yeah. Some of the advantages, you can operate with a lower DC voltage because you don't have that big long line. You can afford to have a bit more current, and yeah, you probably don't care too much about your DC side filtering, so it makes the design a bit easier. All right, so moving on into the converter operation. So the main building block of the LCC converters is this 6-pulse bridge. So you can see the circuit diagram down there. So it's made up of 6 thyristor valves and a 3-phase transformer. So in the context of HVDC, these thyristor valves don't have to be a single thyristor, right? These can be made up of multiple thyristors in series. And we've got, on one of our poles, we've got 66 in series to make up one of these valves. So it's, yeah, but just to show that's, yeah, we've representing it as one device here. So yeah, so what is a thyristor? It's an electronic switch that conducts current in one direction. It turns on when you have a positive voltage across it and you give it a gate pulse. This is your gate connection here. And it turns off when its current goes to 0. So this is the key point. You can't make a thyristor turn off. You have to force it externally to turn off. So that causes a lot of the problems that we have with the LCC. So the VSC uses the IGBTs, which you can force to turn off, and that solves a lot of the problems. Yeah, so a thyristor is basically just a diode, but you're able to decide when it turns on. That's the difference. Okay, so how does this converter operate? So we number our valves like this: 1, 3, 5, 4, 6, 2. And we'd start with valves 1 and 2 conducting. So you can see we've got current coming in on red phase and then coming back on blue phase. And yeah, so at each moment, 1 thyristor from the upper row and 1 from the lower row are on. So we'll always have that. And then we'll move further through the wave. We'll turn on valve 3. So we do this 60 degrees into the cycle of the AC wave. So what that will do is we've now got 3 valves conducting. So we've sort of got 1 and 3 sharing the current. So we've got current coming in on red and yellow, and then all coming back on 2. So 1 and 3 are sort of sharing. And if everything's right and the AC waves that you're feeding the converter with are nice and balanced, once the yellow phase voltage exceeds the red phase voltage, it will cause the current in the thyristor to go to 0 and turn it off. And if that happens successfully, that's called commutation. So going from one valve to another, it's commutation. So all's gone well and 1's turned off. So now we're operating with valves 3 and 2, and then we'll wait another 60 degrees. We'll turn on valve 4 with our pulse, our gate pulse. And then if everything's all good, valve 2 will turn off by itself because of the AC system turning it off. So you can see right now why you need an AC system, you know, why you can't do a black start with the LCC. Because if you don't have this AC system to turn off that other valve, you'll get what we call a commutation failure, and the converter will cease to work. Yep. Okay, I try not to put too much formulas in this presentation, but I think we have to have at least one. So the DC voltage of the converter can be controlled by the firing time of the thyristors. So we use a parameter called alpha, the delay angle. We can vary alpha between 0 and 180 degrees. And in this formula, E is the AC phase-to-phase voltage. So because it's cosine, when alpha is 0, which means we're basically firing the thyristor as soon as we can, we will get the maximum voltage. And that voltage is called UDI naught. And that voltage is 3 times √2 times the phase-to-phase AC voltage divided by pi. So it comes out to about 1.35. So you just need to remember 1.35 times the phase-to-phase voltage. That'll give you your ideal DC voltage, no load. And then as you increase alpha, you'll be able to reduce your voltage. So it shows you with the, when we're operating at 350 kV, our alpha is usually about 16 degrees. But if we want to go to that 250 kV, we increase it up to about 30, 35 degrees. So yeah, that shows you how you've got your control over the voltage there. So the way we do it, we fire the rectifier with the alpha between 0 and 90. So I was telling you about the rectifier before. At the inverter, you wait later, you fire that at 90 and 180. So that's actually on the negative side. So on the inverter, you actually get a negative voltage compared with the rectifier. But the way you build the converters is you actually put the inverter upside down to the rectifier. So the difference between the New Zealand scheme and in the North Island, all the thyristors point to the roof, and in the South Island, they all point to the ground. And then when you fire one as an inverter, the voltage negative, so they cancel out. So you end up with a kind of like a, say, just for argument's sake, a positive voltage at the rectifier and the inverter that you can directly control. And you can see here, we can then choose how much DC current we get through our transmission line by changing this voltage difference. So it's kind of like angle difference with AC transmission lines, but generally the way it's done is you hold your rectifier at your transmission voltage, and then you reduce it at your inverter depending on how much power you want to draw. So in our scheme, we'd hold our rectifier at 350 kV, and the inverter would be at some voltage lower than that, depending on how much power. So yeah, so say 340 kV, that might be about 100 megawatts or something, and it can get down to about 330. Yeah, it depends on your transmission line resistance, how far down it goes. So that's how you can control how much power you send with your firing pulses. Okay, it's worth mentioning reactive power with LCCs. So you can see with that alpha, we're waiting as the voltage comes up, we're waiting until we fire our thyristor. So inherently, we're drawing current out of phase with voltage. And that's, that means reactive power, right? Like if you draw current in phase with voltage, that's all real power. But because we're delaying it, we are going to have some reactive power. So yeah, so it's kind of similar to power factor. And it means whether you're rectifying or an inverter, you will consume reactive power from the AC network. So the rule of thumb is it's about 60%. So if you're sending 1,000 megawatts with your DC link, that means you're going to have to supply 600 megavars of reactive power at each end, which is a bit of a it's a real Achilles heel of the LCC, because that's a lot of capacitor banks to do that. So you need a lot of area in the substation to have that, and lots of filters, lots of circuit breakers, lots of switching. All of those issues, all of those things cause issues, wear and costs. So it's one of the main, one of the real key disadvantages of the LCC. The other problem is harmonics. So because we showed the 6-pulse converter before, and we'll go into 12-pulse, but we're not producing perfect sine waves here. So we're going to have harmonics on the DC and the AC side of the converter that we're going to have to filter. So this is just showing you the waveforms for a 6-pulse converter. So you can see this is our DC voltage here. Where we're starting at the peak here, this is where we've got the 2 valves conducting. And then there's a short period here where we've got 3 valves conducting. So that's where it's swapping over between the 2. then we're back to 2 valves conducting. So you got 2 valves, 3 valves, 2 valves, 3 valves, 2 valves. So this the time that so you can see where we're waiting with our firing angle until we turn that other thyristor on. That's the firing angle alpha, which we talked about, but then there's also this parameter called the overlap angle, and that's the duration of time it takes for the current to swap from one to the other. And yeah, that's generally a function of your converter transformer leakage reactance, but there's a few other things you can change, but it is a desirable characteristic. You do want to have some time for that. Yep. And you can see our currents here are pretty horrible. They don't look anything like a sine wave at all, so we're going to need some serious filtering on the AC side. Yeah, so as I said, AC side current's not a sine wave. For a 6-pulse converter, characteristic harmonics on the AC side are 6n plus or minus 1. So yeah, the harmonics we get are 5th and 7th, 11th and 13th, etc., with decreasing magnitude as order increases. So the 5th would be the worst, then the 7th, and then 11th, 13th. It's also true for the DC side. Voltage and current isn't perfect. For 6-pulse converter, characteristic harmonics are 6n on the DC side. So that's, we've got 6th, 12th, 18th, 24th, and it gets better as the harmonics go up, less magnitude. So the 6-pulse bridge isn't great. You've got, you've got limited power within that topology, and you've got the low order harmonics, which are really hard to filter. So I'm talking the 5th and the 7th there. You need really big capacitors and reactors in the filter banks to hit those frequencies, which are expensive, and not that economical to build up to the really high voltage levels. So what you can do is connect 2 6-pulse bridges in series and make a 12-pulse converter. So the good thing with a 12-pulse converter is you can have your higher power rating. You've got your 2 6-pulse bridges, and your harmonics go up to 12n plus or minus 1. So our worst harmonic then becomes the 11th. We've got 13th, 20th, 23rd, 25th, and the DC harmonics are 12n, so 12th, 24th. So those 12-pulse harmonics, they're generally lower magnitude and a higher order, and it makes them much, much easier to filter than what you'd get with a 6-pulse converter. So this is how you do it. So you can't just have 2 6-pulse bridges connected with the same vector group on your transformers, because then you'd just add up. You'd still have the same 6-pulse profile if you did that. You need to introduce a 30-degree phase shift between the 2 bridges. And you just do that with a delta connection. So on all 12-pulse converters, you'll have one bridge will be star connected and one will be delta connected, and that's so you can get your 30-degree phase shift to offset the converters. It shows you what some of the currents look like in the transformer now. So this was just what we'd have with a 6-pulse with a YY connection. And then we've got our, this is what the current looks like with a Y delta. If you've just had a 6-pulse, and then if you combine them together for the 12-pulse, this is what we get. So you can see it's still not great. It's definitely not a sine wave, but it's better than a 6-pulse, much better. And I thought I'd include some real measurements. So this is just a screenshot I took a couple of days ago on pole 3 at Benmore. So you can see this is our AC, 3-phase AC waves up the top. This is the 3-phase current going into the converter. So you can see those steps that we had on the graph back there. This is the DC voltage. You can see it's definitely not constant. If you think DC, it's like, no, it's not perfectly DC. There's a bit of ripple there. We're only talking sort of 3 kV here on 350, so it's not too bad. And this is our DC current, and you can actually see that characteristic where we've got the 2 valves conducting, 3 valves, then 2 valves, 3 valves, 2 valves. And yeah, the ripple on the current's about 25 amps on 1,000, so it's pretty good. Okay, now we'll look at some of the station equipment for LCC. So this is sort of the basic circuit diagram for a 12-pulse converter monopole. So for the New Zealand scheme, we've got 2 of these basically, but one's connected on the negative side. So On the AC side, you start with your AC filters. So these AC filters will provide your megavars for the converter, but they'll also provide harmonic filtering to cancel out those harmonics. Then you've got your converter transformer. They're absolutely key to give you that phase shift you need for the 12 pulse, or for one of the 6 pulse converters, but then also to give you that leakage reactance for the overlap angle. You need to have that, so the transformer does that for you. Then you have the smoothing reactor on the top. So this is to help with that DC current to smooth it out. And this also contributes towards your minimum power limit. So I mentioned the minimum power before. That's basically the lowest power that you can go before you get discontinuous conduction. So you really don't want to get discontinuous conduction. So the bigger your smoothing reactor is, the lower you can go before you hit your minimum power limit. So it's about 5% what we've got. So our minimum power on pole 3 is 35 megawatts on a 700 megawatt converter. So it's not too bad. But if we double the smoothing reactor, we could maybe reduce it to 25 or something like that. It's so that's one of the key design characteristics for the smoothing reactor. And then last but not least, we have the DC filter. So that helps out with your DC voltage. And that's mainly for the transmission line, acts like a big aerial, and if you've got too much harmonics on the DC side, you can end up with interference, especially if you're going near cities. But it's not so much of a problem these days with most communications going to fiber optics. But back when everything was copper, they used to have issues with harmonics on the DC side causing like audible rings in telephones and stuff like that. It's with our characteristic harmonics, 600 hertz, you can hear that pretty good with the human ear. Okay, so we'll just go through some photos. This is a picture of an AC filter bank. So you can see it's made up of, got some reactors here, we've got some resistors stacked up, and some capacitor banks in the back. So you can have single order, double order, triple order. They're basically just combinations of RLC components with some surge arrestors and CTs in there. So there's a big art with Hvdc design is the AC filter design. There's all sorts of compromises and that you have to take into account. But yeah, you usually end up with certain configuration. Converter transformers. This picture is of a particularly large one. I think this is from an 800 kV scheme. You can see those bushings are extremely long. There's no way this transformer would pass the seismic requirements for New Zealand, so I don't think we could ever have one here, but in a non-seismically active area, you might be okay. So there's a few different configurations you can have for your converter transformers. You can do single phase 2 windings, so that's when you just have single phase transformers and 1 valve winding. So with this configuration, you would need to have 6 converter transformers per pole to get your 12 pulse converter. The other way is single phase 3 windings. You can have your, you can feed the whole 12 pulse converter per phase with 1 transformer. This is what we've got in New Zealand. So there's 3 converter transformers per 12 pulse group here with this arrangement. You can do 3 phase 2 windings. So with this way, you'd have 2 converter transformers. Again, you start to limit your power because you can only make a transformer so big to handle a certain amount of power. So generally, you'll find for the bigger schemes, especially like the schemes in China and India, you have to start to go to like 2 winding transformers just to actually physically fit the rating in. But yeah, this would be 2 transformers, that configuration. Another point to note is the what's different between HVDC transformers and AC transformers. So the converter transformers are special. They're not just like a normal AC transformer. They have a lot more insulation in them, and in the form of paper usually. So in an HVDC transformer, you have a lot more paper than what you'd find in an AC transformer, and that's due to the DC voltage stress. So on a LCC HVDC, your valve windings must be insulated for AC and the DC as well, so you have to add extra paper in there. And they also have to deal with the harmonics. So we saw those harmonics that were going into the converter, that's going through the transformer, so you've got to deal with that. And you generally need a really big tap changer on a HVDC. So we can change the voltage with the firing angle, but there's certain firing angles that we like to operate at, because if we increase our firing angle too much, we start to consume a lot of reactive power, and it's not very nice. So you can sort of account for that with the big wide tap changer range. So you could say if you went to reduce voltage, maybe you go up to 30 straight away, but then as you tap down, you could start to pull your alpha back and get back into that area where you want to operate. Yeah, so for our scheme, we've got a 33 taps on our converter transformers, which is quite a lot more than you'd find on a normal AC transformer. Yeah. It is worth noting that for some VSC schemes, if you use the symmetrical monopole arrangement, you can just use a normal AC transformer. And yeah, Les talks about it in his presentation. But that's the one exception. If you've got a symmetrical monopole VSC, you don't need a special HVDC transformer. Okay, so thyristors. This is what they look like. Yeah, they generally come in 4, 5, or 6 inch. We use 4-inch thyristors on pole 2 and 5-inch on pole 3. The really big schemes use the 6-inch ones, but you can see how the current goes up. They can take a lot of current because these devices are all connected in series, right? You never have them in parallel because the power electronics generally don't really like to share current that well. You can have these the positive temperature or negative temperature coefficients where if one side gets hot, it actually takes more current, and then yeah, so that's no good. So all the current has to go through each device, and the voltage is shared across them. So these thyristors are probably good for a couple of kV each, or maybe the 6 or maybe 5 kV. Yeah, and you just series them up to get the voltage rating that you need. This is showing a light-triggered thyristor. So this is probably one of the newest sort of technological changes on the LCC. LCC's been around since that first Scotland link, or even the Thyristor LCC's been around since the 70s. But yeah, only sort of in the recently we've gone to these light-triggered thyristors. So you used to have the electrically triggered, where you had a gate, a metallic gate that you'd put a voltage into, but now we can go to these light-triggered ones, which does remove some material off the valve and theoretically makes it a bit more reliable. And we've got light-triggered on our latest pole, but we're still using electrically triggered on our older pole. You can see the fiber optics go straight into the middle of the thyristor there. So this is a valve module that you'd find in a valve hall. So I said, each one of those thyristors we were looking at on that 6-pulse bridge is actually made up of lots of thyristors in series. So you can see the thyristors stacked up here. We've also got some snubbers. So each thyristor will have a snubber, the RC circuit, to help with the switching, sharing the voltages. And then we've got these reactors at each end as well. So that's to help with smoothing out the current during the switching. So the way you build it, you start with a thyristor, you add it into a module, and then you stack up your modules to get what you need. This is showing basically how the firing pulses get in. So we have part of the controls called the pole control, which decides the firing angle. That then tells the VBE to send the pulses. This stands for valve-based electronics, and then the valve-based electronics has fiber optics. This is all in the control room here, and then you've got fiber optics from the control room out onto the thyristor stacks to each thyristor. And yeah, if you've got the electrically triggered, these fiber optics have to go into a little box for each thyristor, which converts the fiber pulse into an electric pulse. But for the light triggered, you can go straight from the VBE into the thyristors, so you can see how you're improving the reliability a little bit there. It's showing you the complete converter there. Valve cooling, so the thyristors, they're pretty low loss, but they do get hot. And when you're sending 1,000 megawatts, it's not unsubstantial, the amount of heat that you've got to dissipate. So they're generally water cooled. The thyristors are sandwiched between heat sinks, and the heat sinks actually conduct the line current most of the time as well. So you pass water through them basically on plastic pipes. So the issue with that is with your pumps and your fans, and that this is all at ground potential, whereas your thyristors are at high voltage. So you have to use what we call deionized water, which is water that's had all the minerals and impurities taken out. So that really pure water is actually a pretty good insulator. In that case, you're okay. You're not going to cause any shorts. But if you ran tap water in this system, you'd basically short out your converter through the cooling system. So one of the main jobs of the valve cooling is to keep the conductivity really low. We do that with this resin. There's a tap off that's cleaning the water all the time. And you monitor the conductivity in real time, and if it gets too high, you have to trip. It's a picture of a wall bushing. Yeah, we need quite a lot of bushings in HVDC to get into the converter hall and get out again. This is a smoothing reactor. Again, this would be no good in New Zealand. You can see it looks like it would fall over quite easily, but yeah, they're required on the DC side to reduce your current ripple, limit the rate of rise of the current. It's to help your thyristors and to maintain your DC current continuity when you get down to those low power levels. And this is a DC filter. It's basically the same, pretty similar arrangement to the AC filter, except you're just going for those different harmonics. You know, another thing with the DC filter is a lot of schemes you don't actually have to have the DC filter in. We're able to operate without the DC filter on our scheme. We don't, but if we had a fault in it, we could switch it out and still operate. You can't do that with AC filters. AC filters are critical. It's sort of the Achilles heel of the LCC. If you have too many AC filter problems, you can severely limit the amount of power you can transfer. All right, so now I thought we could try do a bit of a virtual site tour of Benmore. That's the converter station in the South Island of New Zealand. We'll see how it works over the screen sharing, but yeah, hopefully it works all right. So yeah, so Benmore, yeah, the scheme in New Zealand is the LCC Bipolar scheme with earth return, rated at 1200 megawatts, plus or minus 350 kV. Our older pole 2, was commissioned 92. That's 700 megawatts ABB, but the power is limited to 500 megawatts by a single cable over the Cook Strait. Pole 3 was commissioned in 2013. That's a 700 megawatt converter manufactured by Siemens. And yeah, we've got 220 kV AC at both the South and the North Island that it connects between. Okay, let's try this out. Is that working okay?
Yeah, it's a bit jittery, but it's still fine.
Okay, that's great. Yeah, so yeah, so this photo is taken on top of the Benmore Dam, so you can see the HVDC converters down here. We've got pole 3 on the right and pole 2 on the left, and all of this gear out in the yard is pretty much AC filters. So you can see how much space you need. Like these are all the converters are within these buildings, but we need more than, you know, double the space of what the converter halls take up in AC filtering to service the converters. We'll go down to pole 3. Yeah, so this is, we'll start on the AC side of the converter and go over to the DC. So you can see this is our AC connection coming in here, 220 kV, 3 red, yellow, blue. This is the spare converter transformer. So as I said before, we've got the single phase 3 winding transformers. So this is the valve star and the valve delta is the small bushings. And the converter transformers fit in these bays here. We've got these doors on, so you can't see them very well, but yeah, they're in there. I'll go over to pole 2. So these are the pole 2 converter transformers here. They've got the connections coming in on the top, 220 kV. Yeah, we've got a little bit of filtering on the AC side. That's what these reactors are here for. The main circuit breaker. We'll pop over and have a look at some of the AC filters. So these are some of the older AC filters we have, filter 3 and filter 4. So you can see they're basically just combinations of capacitors, reactors, and resistors. Yeah. All right, we'll go to one of these. This is what the control room looks like in pole 2. Just some panels, nothing too interesting really. HMI desk over there. This is the valve-based electronics. We've actually replaced the valve-based electronics since these photos were taken, so that's all shiny and new now. This is the valve cooling for pole 2. You can see your 2 pumps down here. You've got some gas suppression there for the control room. And this is sort of the atrium area going into the valve hall. So the pole 2 valve hall's behind these doors here. So I've got a separate one for the valve hall. So this is inside the pole 2 valve hall. It's the ABB one. So you can see we're sort of looking at the AC side here. All these bushings coming through are the AC connections. So on the bottom we have our star connection. On the top we have the delta. And you can see how they connect onto the converter here. So we've got actually 4 thyristors in here. So of the 2 6-pulse converters stacked up, we've got the highest voltage on the bottom. So it's 350 kV on the bottom. Then we've got our star connected point coming in here for this top side 6-pulse converter. And then the top half is the bottom side 6-pulse converter, which has got the delta connection. And it's repeated for all 3 phases. So this is called a quadra valve. ABB call it a quadra valve. Siemens call it a quadruple valve. Same thing. You can also see these arrestors over each valve. It's to protect it during transients. And this is our DC coming out through this big bushing down the bottom here. So it's tapped off the bottom. This is our 350 kV DC. And the top is connected to the neutral connection. So that's going through this tiny little bushing up here. That's only, doesn't have to be rated for the full voltage. Cool, we'll take a quick look in pole 3. This is the newer pole. There's control desk and a bunch of panels. Nothing too interesting there. This is the valve cooling for pole 3. So you can see our 2 pumps here, duty and standby. So you only ever have one running, and if there's a fault with it, it'll swap over to the other one. You can see the pipes going into the valve hall there. There's water in, water out, and then it goes under the floor to go to the coolers out the back. So I'll show you the coolers when we go to the DC side. And we'll have a look in the valve hall for pole 3, or actually I'll just show the this one. This is like the atrium area for pole 3. You can see this device here, we call it the Chrysler. That's the elevated working platform for working on the valve during the outage. So this stays parked up 361 days of the year and comes out for 4 days during the annual outage into the valve hall. So have a look in the valve hall. This is the Siemens valve. See, it's quite a bit different than the ABB valve. They sort of have it around the other way. And the other key difference is that the delta connections are made inside the valve hall for pole 3, and for pole 2 they're made outside, and then they have bushings coming in. So the Siemens design has less bushings, but you do need a bit more room in the valve hall to make this delta connection up the top. But it's exactly the same design, really. I mean, 30 years newer, but it's the same circuit diagram. Yeah, the high voltage on the bottom. you've got your, you know, this is your star connected coming into your high side 6-pulse converter, then you got your low side 6-pulse converter that's connected on the delta, and then the neutral on the top, and repeated for each phase. Yep. Cool, so we'll just go out to the DC side, into the DC yard. So this is pole 3. So the high voltage DC bushing's behind the smoothing reactor. You can't quite see it there, but there's the smoothing reactor. You can see our one's definitely got a bit more burly design for the seismic with the thicker insulators, and it's a bit more squat, and it's also got this rocking base for the seismic issues. We see some special HVDC equipment that you don't see very often. There's a voltage divider here, so you can't just use a normal VT for HVDC. You've got to use voltage dividers. That's to measure the voltage, and to measure the current, we use these things called current shunts. This is on pole 3. We use current shunts. It's basically just like a resistance in series, and you just measure the voltage across it. So pretty simple, but it works pretty good. You can see the DC line in the background there with the 2 poles. We'll cruise over to pole 2. Here's the pole 3 reactor there. Here's the cooling. This is the cooling fans for the valve cooling. There it comes outside. This is the DC filter here. So that's the capacitor bank for the DC filter. And we've got all these other components here like reactors and resistors. But again, as I said, if we had a failure in here, we can actually switch it out and continue running. Yeah. We also have some switch gear here. If a pole trips, we can isolate the neutral. Yeah, and there's the DC line in the background there. So the connections are made up in the DC yard here, and then this line heads up to towards the North Island. These here are just for the HVAC in the building, so the air conditioning and the valve hall mainly. But yeah, that's pretty much it for the tour from the armchair. Yeah, that's the end of my presentation. Yeah, thanks everyone for sticking around and watching. But yeah, I'll hand it over to Maddie. If there's any questions, I'm happy to attempt to answer them.
Thanks, Mike, and that tour was really great. I'm sure that's the closest anyone in Australia's got to going overseas in a long while, so no, it was good.
I thought it could be good given the times.
Yeah, I think it's a fair while before anyone will get to New Zealand. We did have one question, and I had a couple questions as well. The first question is, I think, about the triggering. So with the electrical triggering on the older pole, how high a voltage do you have to use for the pulse voltage for triggering on the electrical side? And then for the optical trigger, what is the optical frequency range?
All right, those are some pretty tricky questions. I think it's I think for the pole 2, the electrically triggered, the voltage is not that high. I think you're sort of talking. I'm pretty sure it's less than 100 volts. I couldn't tell you the exact value, but I could definitely find out if I needed to. But yeah, there is an issue with the pole 2 system, and that is you need auxiliary power to provide power for that firing pulse, and that's derived usually with the voltage over the converter. So sometimes you can run into problems if the voltage goes nasty over the converter that you might not have enough to send a pulse. But our valve's designed really good. We haven't had any problems with that, but it is one issue with the electrically triggered design. In regards to the optical, I'm not sure what the frequency is, but I'm pretty sure it's red, so it would be around that frequency. I do know for the firing pulses, it's very high intensity light. When we're working in the valve-based electronics, you have to wear special laser goggles in case you somehow expose yourself to one of the firing pulses, because they will definitely damage your eyes, the level of light used.
Oh, awesome. Thanks, Mike. Then there's a follow-up question, I guess a more general question. Can VSC HVDC contribute to system strength?
It depends what you mean by system strength. So generally, it's sort of thought of as no, but you can provide what they sort of call synthetic inertia, and our link kind of does that. We've got a modulation called FKC, frequency keeping control, and it makes the DC act sort of like an AC line. So if the frequency goes down in one island, it will say it's going down in the receiving island, it will automatically increase the transfer to try and prop it up. But if you're talking about short circuit ratio, then no.
And I might slide in my question because it's a bit related to that. For the link, what sort of system strength levels or like short circuit ratios does the link need to operate on the inverter side? Is there a particular minimum fault level that it needs?
Yep, so there's a rule of thumb, and that's about 2. So they call it the ESCR, equivalent short circuit ratio. Yep. And yeah, basically, the more synchronous machines you've got nearby, the better. Wind farms, solar doesn't count. So that's sort of, I think, probably where the LCC is going to be really eclipsed by the VSC as the grid gets less of that traditional generation in it. LCC is going to become less and less appropriate. You start to have really serious problems with commutation failures once you get to these really weak grids.
Yeah, and with the New Zealand link, do you think into the how many extended commutation failures have you had, and do you think you'll have more as more IBR connects, or do you have enough synchronous generation that you think it will be okay?
Yes, so there is a bit of an issue with the New Zealand system, and that is there's not a lot of generation in the lower North Island where the link terminates into. So we're at Haywards, where I'm sitting now. It's we're pretty much operating as an inverter about 70% of the time, as I said. So there's not a lot of synchronous generation around, but what we do have is synchronous condensers. So we've got 8 synchronous condensers here on site, and they basically perform that task for us. But again, they're very onerous to look after. Like I think the budget for us to look after our entire bipolar, including both sites, is about the same as the budget to look after the 8 synchronous condensers that we have. So VSC is definitely really desirable from that point of view, not having to have all the filter banks and condensers and stuff to support the transfer.
Cool. And
but sorry, yeah, we do get commutation failures, but they're not. It's not really an issue. Like it's just a brief blip, and everything's back to normal again.
Yeah, so it can ride through those and then eventually commutate again. Does it usually? Like it doesn't trip the link.
Yes.
So, yeah.
I thought I might get asked this question, so here's a commutation failure. So you can see this is the AC voltage up the top here. This is at Haywards. This is the one 6-pulse bridge current and another 6-pulse bridge current, and this is the DC voltage. So you can see things go wobbly, and the commutation failure actually causes the voltage to be worse than it would have been if you hadn't had the commutation failure. But you can see basically you just block all the firing pulses, wait for all the rubbish to clear out, and then fire up again. And you can see we're sort of talking within 100 milliseconds, we're back online again. So generally you've got enough inertia in the 2 grids to be able to withstand an interruption of that duration.
Awesome. We've had a few more questions. Does deionized water cause any corrosion issues?
I think it's actually better. We don't seem to really have too much issues with corrosion. We do have an issue. There is an issue on our you can get an issue with build up. So when you've got but that's due to the DC voltage. So the valve cooling the water sort of has a DC voltage put across it, and that causes corrosion where the current comes from the from the metal into the water, and build up where it goes from the water back into the ground or wherever it is. And you can have these sort of build-ups occur, but it's very minor. We have to clean. We have some of these things called grading electrodes that they're sort of sacrificial elements. They're made of platinum to try and reduce the effect, but they still do require cleaning every outage at the moment. We are trying a few bits and pieces to change the chemistry of the water to try and to fix it up, but to be honest, the current scheme isn't too onerous. So yeah.
Awesome. And another question, any thoughts on the challenges with the sun cable? So the 3.2 gigawatt HVDC cable proposed between the Northern Territory and Singapore.
Yeah, I know about that project. It's just a absolutely phenomenal length of cable. It just seems like almost an order of magnitude longer, than what's been done before. I think technically it can work. It's just that it's such a long cable, and if you have any sorts of faults, cable faults are really, I mean, like a land cable fault is bad, but a submarine cable fault's even worse. They're really hard to deal with. So I think they'd have to be really careful with the design of the cable. They'd want to make it extremely robust, I would say, to avoid any sort of electrical problem. But then you also have the problem of people hitting it with anchors or trawling or whatever, so that it's covering such a long area. How could you possibly patrol that or keep it stop anyone hitting the cable? Those are the main issues I see, because even with our cables, our cables are 40 kilometers long. I mean, that's like nothing compared to Sun, what they're talking about Sun. I mean, ours is pretty much nothing compared to Basslink as well, but we do a 24/7 patrol over our cables. We've got a cable protection zone. It's in New Zealand law. If you go fishing there or dropping anchor, you can be prosecuted under the law. I just don't know how you deal with that with Sun. Yeah, I guess you'd have to bury it. But then that makes it even harder if you have a cable fault to fix. The cost must be phenomenal too. It's even just we're looking at buying new cables, and it's not a small sum of money.
Yeah, no, it's a huge project. There's another question. Have you seen any issues with the LCC synchronizing to the grid voltage, so the PLL failing? Presume on the inverter side.
Yeah, I guess that sort of manifests itself as a commutation failure, because normally, like, I can say in steady state operation with all the grid voltages nice, no, never a problem. It always works fine. But a lot of the time, that commutation failure I just showed you, that was caused by a fault in the AC network that caused a distortion on the waveforms. So that can either be a distortion in the shape, or in the phase, or in the magnitude, and that can be enough for the controls to miss the firing point when it needs to fire the next one, or wait too late, and then you'll cause your commutation failure. But generally, those disturbances, are short-lived, and you just stop and then you fire up again, like in those traces I showed. So it's pretty good, but yeah, it's one of the Achilles heels of the LCC, is you're really dependent on that AC network being nice and strong and nice and nice and constant phase, and nice waveforms, all that sort of stuff.
Yeah, nice strong grid. I might slide in another one of my questions. Because the New Zealand links a bipole without an earth return, have you ever operated the link, or could you operate the link if one of the cables failed, so as a monopole, or would the earth return current be too high operating like that?
Yes, no, so we do have the earth return scheme,
Okay.
and it is rated for the full current, the full monopole current. It's actually even rated for the overload monopole current. So our electrodes are rated for 3000 amps. So yeah, so we're able to do the full return on the earth return with our scheme.
Yeah, I meant without a metallic return. Sorry, I was just wondering, like, can you operate the link? Yeah, if one of the cables failed as a monopole, I presume you can.
Yes, of course. Yeah. So the say we had one of the cables fail. Well, so we've actually got 3 cables. We've got 2 cables on pole 3 and 1 cable on pole 2. So if we did have a cable fail on pole 3, we'd operate on pole 2 as a monopole, utilizing the ground return 100%. And then we would reconfigure pole 3, or we would switch the failed cable off pole 3. And then we could turn pole 3 back on with just 1 cable. So that would limit us to 1,000 megawatts then. So instead of 1,200, we'd have 1,000, which isn't too much of a big deal, really. So yeah, a single cable failure is not too bad for our scheme. Yeah, but then if we had another one, that would be quite major, because then we'd be down to monopole and we'd be limited at 500. Yeah.
Yeah. Okay. Well, I might wrap it up there. I think that's all of the main questions. So thanks again, Mike. And just a final reminder for everyone that there's all the information about future events and also past events on the NGN website. And as Mike said before, there's all of the past NGN, well, most of the past NGN webinars on YouTube. So if you just search CIGRE Australia, it should come up with our YouTube channel, and you can subscribe to get notifications when we upload new presentations. But yeah, just thanks again, Mike. It was great having you present today. And thanks again for everyone for coming along as well.
No worries. Thanks very much.
Thanks, Mike. See you, everyone.